This is geometry and a section on symmetry. So a figure is going to have symmetry if there exists a rigid motion that maps the figure onto itself. So what do we define a rigid motion as? Well, a rigid motion will be just the types of transformations that we've just talked about: a reflection, a translation, or a rotation. So if one of those three transformations occur and the figure gets mapped onto itself, then we say that it has symmetry. There are also a couple of other types of symmetries. We can have line symmetry, which can also be known as reflection symmetry. What line symmetry is saying is that the figure can be mapped onto itself by a reflection in a line. So this diagram right over here, this is going to be an example of a figure that has line symmetry. If you see, if we put this dashed line, this figure maps onto itself. It reflects onto itself. So this point here is the exact same point is up there reflected across the line. This point is the same here, reflected across the line, and so on and so forth. So this figure would be an example of line symmetry. We can also have rotational symmetry. Another word that rotational symmetry is sometimes called is radial symmetry. And what rotational symmetry tells us is that the figure can be mapped onto itself by a rotation between 0 degrees and 360 degrees. So here, this square right here has rotational symmetry because, as you can see, this first square, we just rotated it 45 degrees, or we rotated it 45 here, and it's not quite back to itself, so we would continue rotating it the whole 90 degrees, and then it is indeed looks exactly like the square was when it originally started. So here the square, we rotate it. So here we rotated it 45 degrees, here we rotated it 90 degrees. And notice that these two figures now are the exact same. So it has rotational symmetry. And you could continue doing that by taking the diagram and continue to rotating it. And every 90 degrees, you're going to get the same exact figure back onto itself. So that is rotational symmetry. So you just have to envision when you have the figure, can you rotate it and get the same figure back? And in this case, with a square, we certainly can. In fact, we can rotate it. Here's 1, 2, 3, 4 different ways to get it back to itself. And that is going to be the next topic, which is called the order of symmetry, which is just discussing how many times the figure maps onto itself. So that previous example of a square, it mapped onto itself 4 times. So our square had an order of symmetry of 4 because it mapped onto itself 4 times. Okay. Then we can also discuss what the magnitude of symmetry is, and the magnitude of symmetry is going to be the smallest angle that the figure can be rotated so it maps onto itself. So what does that mean? Well, for our square, in this example back here, what we were doing is we were saying, okay, so how many degrees do I have to rotate this before I get it back? And we said, well, that's 45, so we rotated it 90 degrees, and we got the same figure back. So for the square has a magnitude then of 90 degrees. Okay. So here we'll do another quick example of one. Here we have a hexagon. Okay, it's 6 sides. So the order of symmetry is how many times can we rotate this and get itself back. So here we start it, and we can rotate it, and there would be itself back, so that's 2. Itself back 3. Itself back 4. Itself back 5, 6, and then our starting figure. So the hexagon here its order of symmetry is 6. Okay? Now how do we figure out the magnitude? Well, it was a little bit easier for us to do the magnitude of the square. Okay, that was definitely a little bit easier for us to do. So now when we do the magnitude of a hexagon, we just need to think, okay, well, how many degrees are there? When we go all the way around in a circle, there are 360 degrees. So 360 degrees, and we'd want to divide that by 6 because we could move it 6 times and map it 6 times onto itself. Okay, well, 360 degrees divided by 6 is 60 degrees. So for this hexagon, it has a magnitude of 60. Okay, so that is our transformations on symmetry.